Hey guys, and welcome to our video on trends of properties of the homologous series. Today we're going to be examining and explaining some of the trends in common compounds and also examining and explaining different trends in volatility and solubility. So within this lecture we're going to be going over the trends of firstly common compounds in regards to melting and boiling point, and secondly the trends in regards to solubility. So firstly we'll start with melting and boiling point. And I think firstly it's important to understand what actually determines the strength or the variations in strength in melting and boiling point of different compounds, right? So especially in regards to melting and boiling point, the key determinant of these are the intermolecular forces. So I've got a little diagram here which demonstrates this. So say we have a compound A, right? So A has these intermolecular forces. So it's bound by neighboring A compounds with these intermolecular forces. Basically, when we're trying to melt or boil this compound A, we're giving energy and supplying energy to basically make these A atoms vibrate. So they're kind of oscillating. And then hopefully we supply enough energy and enough vibration within these A molecules to break apart these intermolecular bonds, and we'll get three separate A molecules that are free in space. So if you can imagine, if they're tightly bound, maybe in like a solid, and we supply enough energy, so we heat up compound A, and now we have very little intermolecular bonds or weaker intermolecular bonds. We've broken those strong intermolecular bonds, and now compound A is freely available to float around, and now it's a liquid, right? So basically, we've melted compound A. So the take-home message is the stronger this bond here, or the stronger the intermolecular bond, the more energy or the more temperature we have to supply to break apart and cause it to melt or boil. So the first main trend that we need to go over in regards to melting and boiling point is that, especially for non-polar compounds, as the length of the carbon chain increases, the melting and the boiling points of the compound will increase. There are a couple of reasons why this happens. So firstly, there's a greater surface area in between neighboring molecules that can overlap, and especially something to consider is that the linear version of a compound will always have a higher melting or boiling point than the branched form, and also that because we have these longer carbon chains, we have more electrons, more overlap, and also the strength of the dispersion forces between the neighboring molecules will also be stronger. So that's another reason why, as the length of the carbon chain increases, the melting and boiling point will also increase. Now I've got just a nice schematic that shows this. So on the left, I have obviously a very long molecule, and on the top, I have a shorter version of that molecule, and I have a branched version. So clearly, you can see between the neighboring molecules in this first compound here, there are a lot of intermolecular forces that are present, and also there's a greater surface area or overlap, right? So these little dispersion forces, whilst individually aren't very strong, collectively, since there's so many of them, will create a strong intermolecular bond. And referring back to what I said earlier, the higher the melting point and boiling point, the stronger the intermolecular forces need to be. When we compare this with this compound here, although it has the same dispersion forces, clearly there are less of them. Thus, for non-polar compounds, the longer the carbon chain is, the longer the intermolecular forces will be, and thus the higher the melting and the boiling point will be. I also mentioned something about branched versions. So this is the linear form. So if you count the number of carbons, the top compound and the branched compound have the same number of carbons, but the top compound is obviously the linear, or when I say linear, just think of line, so straight line, the linear form, and the bottom is obviously the branched version, right? So in the same given, roughly the same given space, I can fit 3 molecules, probably even more actually, of the linear molecule, but I can only fit up to 2 molecules of this branched form, and clearly we aren't able to form as strong a dispersion force because there's such big gaps between the molecules, right? So they can't pack as tightly together. So this goes to show. So the main takeaways especially for non-polar compounds, is the longer the chain gets, the higher the melting and the boiling point will be, and the linear molecule will always have a higher melting and boiling point compared to its branched counterpart. So now we'll start our discussion in regards to melting and boiling points, especially when it comes to functional groups. So I'll bring your attention down the bottom here. So you might have seen this before. So hydrogen bonds, as you know, are stronger than dipole-dipole interactions, which are stronger than dispersion forces. Thus, a compound with a functional group that contains or is able to make, hydrogen bonds versus one that's only able to make maybe dipole-dipole interactions will have the higher melting and boiling point. So however, you know these three types of intermolecular forces based on how strong or how many of these a functional group has. That'll determine the melting and boiling point, and we'll go over some examples. There are another couple of takeaways that I need you to take. So the larger the molecule, the smaller the difference in boiling point. So what does that actually mean? So for example, we know hydrogen bonds are extremely strong. An example of a compound or a functional group that can make hydrogen bonds is perhaps an alcohol. Basically what I'm saying in that dot point is, so methanol, which is a single carbon with a OH group, will have a very big difference in regards to the melting and boiling point when compared to methane, which is the alkane version of methanol, obviously without that OH group. However, this is a point of diminishing returns, and I have a slide later that shows this better, but just take my word for it now. This is a point of diminishing returns. As we, instead of methanol, if we have maybe a 10 carbon chain, yep, so we're combining decane and decanol. So 10 carbons with the OH would be decanol, and then decane is just the alkane version of that alcohol. So that one OH group overall contributes a lot less compared to methanol, in which there's only one OH group versus one nonpolar group. And that's something that I'll show in later slides. Also, the presence of the double bond doesn't have that significant effect. You'll actually find that alkanes have a higher melting and boiling point compared to their corresponding alkenes, and that's because they end up stacking a little bit better, and that's something we touched on a previous slide. So here we have an example of what I was referring to earlier. So on the left-hand side, we have examples of two carboxylic acids, and on the right-hand side, we have an example of two alcohols. So I'll just highlight this point using the alcohols, and hopefully you can logic it and hopefully come to the same conclusion using the carboxylic acids, right? So this OH bond is able to make hydrogen bonds, right? And we know hydrogen bonds are very, very electronegative and lead to strong intermolecular forces. Thus, if this molecule didn't have that OH, it would have a proportionally lower melting and boiling point compared to now that it does, right? However, if we look at this molecule at the top, right, it does have an OH. It's not wrong. It is able to make hydrogen bonds, which are very strong. However, if it didn't have that OH, perspectively or comparatively compared to this bond here, it's actually not missing out on a whole lot because it has all this worth of dispersion forces, not dipole, dispersion forces that it can make compared to a non-polar version of this compound that perhaps doesn't have the OH, right? So basically what I'm saying in simple terms is the gap between the melting and boiling point between this alkane here and this alcohol compared to this alcohol and this alkane is going to be less significant. So just to recap, now we know that nonpolar compounds, their melting and boiling points increase as the length of the chain increases. With compounds with some special functional groups, we have an order of strongest intermolecular forces to least strong. You can refer to that table that you may have. There's one later coming on as well that shows the functional group and what type of intermolecular forces that it creates. So we know that hydrogen or functional groups that form hydrogen bonds are stronger than those that form dipole-dipole interactions, which are stronger than those that form dispersion forces. However, now we need to talk about some trends in between these functional groups. So we know that as a general, we can kind of sift them based on what type of intermolecular forces they make, but it's actually important to look into it a little more. So amines, the most significant thing you need to know is nitrogen is less electronegative than oxygen, just pure fact. Thus, the hydrogen bonds that an amine will be able to make will be less strong than, for example, an alcohol which has the OH bond. So thus, for the same number of carbons, an amine will have a lower melting and boiling point compared to a similarly sized alcohol. With esters, their main intermolecular forces are dipole-dipole interactions, so they can't actually make hydrogen bonds. So they will have a proportionally lower melting and boiling point than both carboxylic acids and alcohols. Amides, on the other hand, they can form hydrogen bonds. However, they can also form that dipole-dipole interaction because they've got that C double bond O. So amide will have stronger intermolecular forces than amines. So basically, what I want you to take away: alcohols are stronger than amines because nitrogen is less electronegative than oxygen, so you get that less strong hydrogen bond. I also want you to take in this order. So carboxylic acids will have the highest melting and boiling points because they have both the hydrogen bonds and the dipole-dipole interactions, followed by alcohols, followed by esters. Amides, they're kind of alone by themselves, but you should just remember they do have very high melting and boiling points because not only do they have the C double bond O, they also have the nitrogen with the hydrogen bonded to form hydrogen bonds. I should just also add, in regards to the previous slide, that when you're analyzing functional groups or trends between functional groups, you need to make sure that both the compounds have a similar size or equal number of carbon chain length. So when I said that an amine will have a lower melting and boiling point compared to a similarly sized alcohol, both the amine and the alcohol need to have the same amount of carbons for that to hold true, or similar amount of carbons for that to hold true. As I said earlier, as the length of the carbon chain increases, so will the melting and boiling point. So if you're analyzing two compounds, one that has a huge carbon chain and one that is small, and you're saying, yep, this difference in melting and boiling point is due to the difference in the functional groups, that obviously isn't entirely accurate. And in saying that, the next couple of slides, I've made tables or modified the tables that we've been making in regards to the functional groups and just added the boiling point. And for all of these boiling points, I've chosen approximately 6 or therefore carbons so we can analyze the trends in between the functional groups. So for alkanes, alkenes, and alkynes, they all tend to have pretty similar melting and boiling points. However, alkynes will have a slightly higher melting and boiling point just because they pack a little better. Haloalkanes, as you know, will form dipole-dipole interactions due to the polarity of the halogens attached to the alkane, and thus will have a significantly higher melting and boiling point compared to a similarly sized alkane. So chlorohexane will have a pretty big difference in boiling point compared to hexane. Hydroxyls, as you know, can form hydrogen bonds as well as dipole-dipole interactions, as well as the dispersion forces. Thus, due to the ability to form hydrogen bonds, hexanol, which is an alcohol with 6 carbons, will have a higher boiling point than chlorohexane and hexane. A carboxyl is interesting in that it can make the hydrogen bond, it can make the dipole-dipole interaction, and it can make the dispersion forces, right? Because it has a C double bond O, which can make the dipole-dipole interactions, but it also has that OH group, which can make hydrogen bonds, right? So the carboxyl has kind of an edge on the hydroxyl in that it can make dipole-dipole interactions on top of the hydrogen bonds, right? So thus, you see that hexanoic acid has the highest boiling point compared to all these compounds. So now we'll continue our conversation. So esters, as you know, will form a dipole-dipole interaction and also have dispersion forces. Thus, that gives them a little lower of a boiling point and melting point, and especially carboxylic acids, which can form both the hydrogen bond and the dipole-dipole interaction, where esters obviously cannot form the hydrogen bonds. Amines and amides I like to group together. So basically, as you know, an amide is an amine with the C double bond O bond. It's a bit of a mouthful to say, but thus an amide will be able to make hydrogen bonds, dipole-dipole interactions, whereas an amine will only be able to form just the hydrogen bonds. It doesn't have that extra dipole-dipole interaction given by the C double bond O bond. And thus an amide will have a significantly higher melting and boiling point. Nitriles are also not able to form hydrogen bonds at all because, as you know, although they do have the nitrogen, they don't have the nitrogen bonded to a hydrogen. Thus, they only form dipole-dipole interactions and dispersion forces. So just in your mind, just keep it keep it nice and simple. So just know that amides and carboxylic acids usually have really high boiling points. Esters, amines, nitriles, alcohols, and so on and so forth kind of sit around that a similar boiling point. Due to their bonding nature, aldehydes and ketones can both form dipole-dipole interaction and dispersion forces. So thus they end up having very similar melting and boiling points. Usually aldehydes have a bit of a higher melting and boiling point, but honestly this is not too significant, not something you need to remember. Aldehydes and ketones, their melting and boiling points mostly just increase as the number of carbons increase on either side of the group. So hopefully now you're able to understand how some of the trends in melting and boiling point come to be with regards to these functional groups. And now we'll start our discussion on solubility and how these functional groups kind of affect solubility in certain ways. Before we start, it's really important to understand the difference between the solvent and the solute. Something I like to remember is always just a simple analogy of sugar dissolving in water, right? So if you can imagine, if I have a spoonful of sugar and it's dissolving in water, the water is a solvent, so that is what is doing the dissolving, and the solute is what I add, which is, in this case, the sugar, right? So if something is soluble in another, basically what we're saying is the intermolecular bonds that are present between what we add and what is doing the dissolving, or whatever liquid we're adding it to, need to be stronger than the intermolecular bonds between the individual liquid molecules, or whatever we're dissolving it into, right? And I have a really nice diagram in the next slide to illustrate this point, so don't panic just yet. There are also a couple of factors that affect solubility. So temperature and pressure both have a positive relationship on solubility. So as you increase the temperature and you increase the pressure, you can dissolve more of a substance, and I'll show you how that comes to be. So here I have a quick simple diagram on what I was saying before in regards to the intermolecular forces between the solute and the solvent needing to be stronger than the intermolecular forces between the individual solvent molecules, right? In order for a substance to be soluble. So pretend A is my solute, right? So that is what I'm adding, and I'm adding it into water, or H2O, which is my solvent. So as we know, water tends to make these really nice hydrogen bonds between the individual water molecules, right? And I'll just draw some hydrogen bonds indicated by these dotted lines, right? In order for substance A to be dissolvable in water, it needs to form intermolecular forces that are as strong or stronger than the intermolecular forces present between the individual water molecules, right? So essentially this force here needs to be stronger than this force here. So substances that typically make hydrogen bonds are really dissolvable in water, as well as some substances that form dipole-dipole interactions, and we're going to go over that in a couple of slides' time. So understanding another concept that will help your understanding with trends in melting and boiling point, as well as trends in solubility, is being able to appreciate that a polar compound will have a slight hydrophobic and a slight hydrophilic section. So what does that actually mean? So as we know, this is a carboxylic acid. This section here is the functional group, or the C double bond O and the OH, and this section is polar. The rest of this long hydrocarbon tail, I'm going to mark that in a box, we know that is non-polar. The polar section can form really strong intermolecular forces, namely hydrogen bonds and dipole-dipole interactions, as well as irregular dispersion forces, and the non-polar part can only form dispersion forces, right? Going back to our previous discussion, for a substance to be dissolvable in water, essentially, it needs to have intermolecular forces, stronger than that of the hydrogen bonds and the dipole-dipole interactions present between the individual water molecules, right? So thus, this polar part needs to overpower this non-polar part, right? There are also two fancy terms that are useful in understanding. So we call this polar part the hydrophilic part, or the water-like king. And as you know, to have a phobia of something is to be scared of it. So this is the non-polar part. We call it hydrophobic, right? So essentially, solubility and intermolecular forces are a balancing act between these hydrophobic and these hydrophilic sections, right? So kind of think of them as like two sides in a tug of war, right? If the hydrophilic part is stronger than the hydrophobic part, overall the molecule will be hydrophilic, and same the other way around, right? So for example, in this case, if I were to extend this carbon chain, right? Now, this non-polar part contributes much more significantly to the intermolecular forces of the molecule than the polar part. So thus, overall, the molecule will be more hydrophobic in nature. It's not really important to know how much, like how non-polar a compound needs to be before it's hydrophobic. Just appreciate it in general. Okay, so hopefully that's a little more clear. In regards to the trends for solubility, there's some general trends that we can go over, and then some more specific trends in regards to the functional groups. So, like I said, each molecule has, if it's polar, has a hydrophobic section and a hydrophilic section. And solubility is especially in regards to water. So our conversation really is only based on solubility in water. We'll go over solubility in substances other than water in a couple of slides' time, but for now, let's just focus on water. So with solubility in water, it's mainly a balancing act between the hydrophobic part of the molecule and the hydrophilic. So as you can tell, the longer the carbon chain is before the functional group, the less soluble the substance will be. And conversely, the shorter the carbon chain is before the functional group, the more soluble something will be. Also, solubility, especially in regards to water, is highly dependent on the type of intermolecular forces the solute or the compound that you're adding is able to make. So if we're able to make really strong dipole-dipole interactions or really strong hydrogen bonds, as you'll see in a couple of slides' time is the case for some of these functional groups, these will be a lot more soluble as opposed to something like an alkane, which can only make dispersion forces. So especially with regards to trends in solubility with regards to the functional groups, it's much smarter to remember them in groups instead of going through the individual functional groups. So as we know, non-polar compounds such as alkanes, alkenes, and alkynes form only dispersion forces, which we know are much weaker than the hydrogen bonds that are present between the water molecules, and thus all alkanes, alkenes, and alkynes are immiscible in water. So if you add any of those substances, immiscible basically means doesn't dissolve. So if you add any of those substances to water, it'll form two layers, usually with the alkane, alkene, or alkyne on top because it has a lesser density. Compounds with the CO or OH bonds, so that includes your carboxylic acids, ketones, alcohols, and aldehydes, they're able to form hydrogen bonds or dipole-dipole interactions, not all of them, irrespectively. So the main compounds that are soluble in water, and this is an important order to remember, is that carboxylic acids are the most soluble in water as they're able to form the hydrogen bonds, the dipole-dipole interactions, followed by your ketones, alcohols, then your aldehydes. So you might recall this slide from before, but I've just tweaked it slightly to make it more applicable to solubility. So with amines, it's important to know what a primary, secondary, and tertiary amine is. So in the little space I have above, I'll just draw this. So with a primary amine, you have the N, you have the H, and you have one carbon chain, right? With a secondary amine, this time you have two carbon chains coming off. So I'm going to call this R1 and R2, and you only have one H. And with a tertiary amine, remove that, you have three carbon chains. So you don't have any hydrogen bonded to that nitrogen. Thus, tertiary amines, since they can't form hydrogen bonds, end up being immiscible in water. However, primary and secondary amines, depending on how long the carbon chains are usually miscible in water. So they do dissolve in water. Esters are a bit more interesting. So they form your dipole-dipole interactions. As you know, they don't form hydrogen bonds. Most esters aren't very soluble in water. However, we can dissolve them in organic solvents. So whatever you can't dissolve in water, you can dissolve in something like an organic solvent such as a benzene. So benzene is like an industrial solvent that you can use to dissolve all these non-polar compounds. Amides are a little more interesting. So they have, as you know, they can form hydrogen bonds, and thus small amides are soluble in water. But in regards to all of the molecules that we've discussed, or all of the functional groups that we've discussed, as the length of the alkyl group or the carbon chain increases, the solubility of the compound ends up decreasing. Last but not least, we have the halogens. So although the halogens are polar, they aren't able to form hydrogen bonds. So that's a key distinguisher. As you can see, we have a bit of a trend developing. So bar a couple of exceptions, if you can't form hydrogen bonds, it's very hard for a molecule to be dissolvable in water. There are a couple of exceptions to that rule, as we previously discussed. However, halogens aren't an exception to that rule. So back to that discussion, although halogens have that polar functional group, they can only form dipole-dipole interactions. They can't actually form hydrogen bonds, and thus they're not as strongly attracted to water molecules, and they're a little less hydrophilic and more hydrophobic than the rest of the other classes that we've discussed.